Okay, we'll give people a couple more minutes and then we'll get started. Have any of you logged into the remote lab yet? Anybody tried? Okay, well, let's get started. Hopefully some more will turn up. There's no excuse now for being late, but you never know. So today we're going to cover the second half of power amplifiers. So this will be the last lecture on power amps, mostly covering A, B, and C classes. And next week, you may have seen on the schedule, you'll be doing system integration and maximizing power transfer. That will be the last lecture of new content. The last few lectures after that are going to be a mini exam and some review lectures, some more practice problems, that sort of stuff. So we're coming now to the end of the actual, the bulk of the course content. So hopefully you've learnt a lot so far, and we'll see how it goes. For that mini exam that's coming up, that's going to cover all the topics. So that's only in a couple of weeks now, so it's worth trying to get a little bit of revision in, maybe look over those assignments, prepare a little bit for it. It will be, as I say, it will be like I think it's a 1 hour version of the exam, obviously different questions to what you'll get on the exam, but the same kind of structure. So we have 4 questions covering all the different topics that we've gone through. You actually only have to answer 3 of the 4, okay? And that will be how the final exam works as well. So that's what some people complain that it's maybe not enough time with the 2 hour actual exam limit, but you actually only have to answer 3 of the 4 questions. So we've done that to enable you to sort of pick and choose your favorites and easily finish in time. So first I'll start with a reminder today, the upcoming assessment tasks. I'm sure you're all aware the assignment 3 is due today, okay? So that's midnight tonight, I believe, the deadline. Your second lab report will be due on the 27th, okay? So this is all on the weekly schedule and on iLearn. Again, get working on that. I appreciate you'll be busy with the assignment right now, but get going on the lab report as soon as you can. I noticed we have the next assignment has the same deadline as this lab report, and we haven't even published that for you yet because we've had a few extensions throughout the course. So I'm going to move that whole assignment 4 back a week, okay? So I'll send out an announcement, but that won't be a conflicting deadline, so you have more time to do that. And that should be published up on iLearn probably by Sunday, okay? So don't worry too much about assignment 4 yet, which will be on power amplifiers. And of course, right now we're running the power amplifiers lab. So remember, this is a remote lab. I'm not sure if any of you would have tried it out yet, I'll go into a bit more detail at the end, and if anyone does have questions on this, because it is quite a new concept, feel free to ask, and I can send out the answers to the whole class after the lecture as well. So just to clarify there, you don't need to come into the lab time slots, but you're welcome to. If you want to use the lab computers, come at your normal slot, you can use it, and a tutor will be there for the first hour. Okay, so if you're struggling, or you can't even connect, or there's any issues you want to consult about, come for your regular time slot or any of the lab time slots and speak to the tutor. Okay, but you can do the whole thing remotely. You could do it from home. You'll have to connect to a VPN if you're at home. So I think Binesh has authorized you all to use it, and there's some instructions online and on iLearn how to connect, very simple, and then you can just log in as if you were in the network. So yeah, I'll go over a few more details on that at the end as well, but just be aware of all these upcoming ones, and that assignment 4 is going to be shifted back probably by about a week. Okay? Primary deadline assignment due tonight for assignment 3. Okay, so for today's lecture, we'll go over a little bit of the stuff we covered in lecture 1. We'll just review that briefly. Then we're going to talk about the class AB power amplifier and focus on how that operates and how you can bias that, because that one involves biasing. It's basically a class B with biasing added. And I'm going to give a brief overview of class C amplifiers. We don't focus on those. They're mostly used in RF applications. So those, if you're doing any RF-based courses, that would be sort of primary content, but for us, we're just making you aware of them. We're not really going to ask you any technical questions on Class C. So it's mostly A, B, and AB, because that's the more general use power amplifiers. And you'll see why when we cover those. So just to go over the classifications again, in case anyone missed last week or managed to forget already, we have Class A. And these are defined by their conduction angles. So this one, 360 degrees. If you remember from last week, this looks great, like as in terms of its characteristics there, but the power efficiency limit is quite low. So up to 25% is the best you're going to get out of a Class A. So not used very often nowadays. Depends on the cost of your product. Class B, conduction angle of 180 degrees. We looked at this one last week as well. So you can see obviously this only works for in this case, the positive side of the signal. You can of course put two of these together to cover the negatives as well. And class AB, so this is the between 180 and 360 degree conduction angle. So it's essentially B with a slight bias to shift it up, okay? And we'll go over why that's needed in a minute. And finally, Class C. Okay, so this is less than 180 degrees, less than pi conduction angle. You can imagine you lose quite a lot of your input signal there, which is why these are only used in RF applications typically. And again, we'll cover that at the end of the lecture. And you remember we discussed a lot about the power efficiency of these. That's critical for a power amp because there's a lot of power going into this. And Class A being the worst efficiency, Class C can actually be up to 90%, so the best efficiency, but of course you lose a lot of signal, you're not operating for a lot of your waveform. And Class B up to around 78%, we showed you, 78.5. Okay, so just to go over the transfer characteristics again, and you should have seen this I think in the pre-quiz for the lecture. So your Class A, there you have a typical Class A circuit here on the left. 2 transistors, one's acting as a current source essentially, the other's an emitter follower, and this is the transfer characteristic that we get from that. The key things to note on your transfer characteristic is of course your saturation, so your maximum output is going to be limited by your power supply minus your VCE saturation voltage, because of course we want to keep these in the active region to amplify correctly. And your negative side can be limited by either the Q2 saturation or the Q1 cutoff. So if you're drawing too much current, depending on the size of your load, on the load resistance there, that can actually create the cutoff voltage. So we went into that a little bit more detail last week. We won't cover it much more today. And then your limit to get your maximum output swing there for your full class A conduction angle is just this equation. So that's essentially ensuring that we're limited by Q2 saturation rather than Q1 cutoff. Make sense to everyone? Happy with class A? Then we have class B. And as I mentioned, the issues with class A, poor power efficiency. You also notice that there's that VBE1 offset, okay? So that can be a bit of an issue as well. Class B doesn't have a direct offset for the whole curve, but you do have the deadband, okay, which is a bigger problem. And as you remember from last week, that leads to crossover distortion. And that's because these transistors in the quiescent state are not operating. They're both cut off. It's great for power efficiency when you've got no input, but it means you need 0.5 or more, depending on your transistor, to get any output to occur. And then we have a typical transfer characteristic after that, with a slope of approximately 1 and limited by transistors remaining in the active region. Okay? So this one's suitable if you're not worried about those low voltages. If maybe everything you're doing, all of your inputs are quite high voltage, it's not going to be a problem. Okay? But if you're going to have swings that do cross the positive to negative, and you do have a lot of small voltages that you care about, and for example audio, then you really need to take care of that deadband and eliminate it. And that's the effect it will have on in the time domain on your input and output signals. So we get this nasty crossover distortion element here. So it gets unwanted frequencies in the output and basically leads to poor fidelity, which is not typically what you want in your amplifier. So now we move on to the main topic for today, the class AB amplifier, probably the most common power amp. You'll see that it compromises between kind of the A and B. So here we have a typical circuit for that, more of a theoretical one, where we just have biasing for both of our transistors, represented by this bias voltage VBB, and as it's equal both sides, we just define these as VBB over 2 on either end, okay? So that's setting up both of your transistors to be just on the edge of the active region, ready to operate. So this can essentially eliminate that crossover distortion. But the downside, of course, is that some small amount of current is going to flow even when we have zero input. So not as bad as class A, where we have quite a lot of power. In fact, maximum power can be flowing and dissipated at zero input. But here we do have some. So unlike class B, where you have 0, right? So if you leave this idle for a while, it's still going to drain your battery. It's still going to consume power. Just from the diagram here, you can look at the current relationships. So we can say that IN is going to be equal to IP because of the directions of the current there. And this will be equal to your quiescent current, which you can calculate using the diode equation. Okay, so just your saturation current, your VBB, your voltage here is VBB over 2, so it's VBB over 2 VT. Okay, so that equation hopefully is very familiar to all of you. We would have covered that quite a few times towards the beginning of the course. So we're going to jump straight in with a class exercise on this. So we have a typical class AB circuit in the top left. Power supply 15 volts, quiescent current, so that's its kind of steady state right now, 2 milliamps, and a load of 100 ohms. Can assume perfect matching of those transistors. What's the required value of VBB to ensure these conditions are met? And a hint will come up in about 15 seconds if you've forgotten the equation on the previous slide, but that will help you out. Okay, there's the hint. Alright, we have at least one submission. That's good. I'll give you another 20 seconds just to finish that up if you haven't already got to an answer. Everybody happy? Yep. Okay, 1.186 seems to be agreement, and that's correct. So for anyone that didn't finish it, I'll just go through that now. So this one's pretty straightforward once you've got that equation. So we're really just using this part of the equation here. We know our IQ, so that is, well, I've zoomed in. Sorry, I'm going back one sec. That's our IQ is 2 milliamps, and that's going to be equal to 10 to the minus 13 over 2 VT. We know our VT, right? That's our thermal voltage. If you're not given it, we can assume 25 millivolts there. Oh. So then we can just divide through by that IS. And just take the log of both sides. And then it's just pretty simple rearrangements. Make sense to everybody? Yep. So pretty straightforward. That's one way to get to your value of VBB. So if those were the conditions you wanted in your circuit, then you can set your DC supplies over here to be 1.186 total. So that would be half of that on each one. So we'll just look a little bit more in depth at how this circuit operates. So we can see our output voltage is going to be equal, let's just get the laser pointer up, equal our input voltage. So if we assume for a positive input, we have our input plus VBB divided by 2, that adds to our input, and then minus VBE for the N transistor, okay? Remember, here we have a NPN and a PNP transistor, so they are different. So that gives you your output voltage, pretty straightforward. Now we can see again just from the diagram, IN is going to be equal to IP plus IL, okay? So that's a straightforward relationship. And again, from the symmetry of this circuit and the fact that we have common nodes here and here, we can say that our VBE-N plus our VBE-P must equal VBB, okay? So now we have we already know our equation here for IQ, our quiescent, is dependent on VBB. And if we use the same equation for IN and IP, or to get our VBEN and our VBEP, we come to this equation here. Okay, so here, this one's got IN, here we have IP, this will give these values, and we have our one for getting VBB on the right here. Okay, so that's just the inverse of the diode equation, which you all just did in that previous class exercise just now, okay? Now with that, we can do some simple logarithmic tricks to show that this actually just means that INIP is equal to IQ squared, okay? Is everyone familiar with these log rules? Yep. So we have the log product rule and the log power rule. So this can be used to get these into simple expressions. So 2 log x is the same as log x squared, okay? And then you can divide through by your VT, which is common in all of these, and you end up with this very simple equation here, okay? If you're not familiar with those, then something to go away and play with. Make sure you understand those. That's just the kind of mathematical tricks behind it. Practice that. As I said, these are the kind of things, derivations like this, we can't ask you in the assignments. There you have to give a correct answer, like a numeric value. But in your exam, you could be asked to show something like this, okay? So make sure you understand the steps that will get there. And the final stage of this, if we combine these 2 equations that we have, we've got one up here, and this one here, where we have the IQ squared term. So if we substitute in to remove IP using this equation, so IN minus IL will be equal to IP, yep. Then we get a quadratic, okay? So here we can solve for IN just using the quadratic formula, yep. As long as you know a value for IL and a value for IQ, then you can solve for IN. Does that make sense to everybody? Everyone's familiar with the quadratic formula? Yep. And that's another one that is probably never going to be given on a formula sheet in any of these, okay? So make sure you are. You'd be surprised how often people will get the signs the wrong way around or something like that. Okay, so that's your circuit operation, how you can calculate the IN current. And with that, you can, depending on what information you have, you could then calculate IP using the same information. You could calculate IL if you didn't need it and you had the other variables. So how does this look as a transfer characteristic? So we looked at A and B earlier, so this is your AB transfer characteristic. So you can see we have a nice, straightforward, for the most part, linear slope of around 1, and we're just limited by our transistors staying in the active mode, so limited by the saturation voltages, and pretty much no offset here, okay? No crossover distortion, or near 0 crossover distortion. It's a very nice transfer characteristic. One thing to note there, under the quiescent conditions, unlike B, where you'll be dissipating 0 power, here we'll have a power of VCC times IQ, okay, that quiescent current. So one thing we didn't really cover last lecture, where we focused more there on the power dissipation and efficiency, how do we calculate these transfer functions, okay? And there are a few ways you can go about it. But probably the easiest way is to work backwards for a given V out and calculate the V in. Okay? So the transfer function is just V out versus V in, done for many, many different input or output voltages. Yep. So if you were to come up with a table, you could do an Excel sheet and calculate the output voltage, input voltage at many different values. You can draw this relationship. Okay? So to step you through that, first assume any value for V out. Maybe in a question you're given that, or you can just start with, let's say, 1 volt, whatever you want, to get your first point on that curve. Then determine your load current, okay? IL here, that's pretty straightforward. V out divided by your load resistor. Using that, you can then determine the current IN. Okay, so that's the quadratic that we just went through, and if you solve that quadratic, you can get to the equation. This, of course, needs knowledge also of IQ, which is normally going to be given to you or can be calculated if you know your VBB. Now that you've got IN, you can determine VBEN, because you've got your IN parameter needed in there. And then you can determine your input voltage, again with the equation I showed you earlier, that simple relationship, Vin equal to V out plus your VBEN minus VBB over 2. Okay? So if you do that, and you wouldn't normally do it all by hand, but if you do that, let's say in a sheet or using MATLAB or any sort of looping formula, you can get all of the points along here. Okay? So let's try it out. So here's the situation, same amplifier as the last question. Here the VBB is given to you, which we calculated before, 1.186. And the output voltage in this case is 0.5 volts. So what's the input voltage? Everything you need to solve this is already on the screen, down in the bottom left. Oh, we have an answer. Good, first person's in. I'll give you a little bit of extra time to finish up, see if you agree with that answer or not. See a few people still calculating. Okay, so I'll go through that procedure just so you can check your calculations against it. So 0.527 is a correct answer. So that's good. So the steps to solving this, pretty straightforward when you've got those equations in front of you. So first, we calculate our IL. So we already know our output voltage. V out is equal to 0.5 volts. We know our output resistance, 100 ohms. So very simple calculation to get our IL equal to 5 milliamps. Once we've got the IL, and we've been given IQ as 2 milliamps, so we can then solve this quadratic. So we have IN squared minus 5 times 10 to the minus 3 IN minus 4 times 10 to the minus 6. That's the IQ squared at the end there. Putting that into the quadratic formula. And then, of course, you have your plus and minus options. Only one of them is going to be positive, and that's the direction we want for this current. So we get IN equal to 5.7 milliamps. Once we have IN, it's pretty straightforward to get the VBEN. So that's your thermal voltage times 24.77, 0.62, and then you can calculate your VI. Output voltage plus your VBEN minus half of your VBB, so that would be make sense to everybody? That's probably the most calculation you'll have on a slide today, so that's good. So we have V out equals 0.5, V in is 0.527. What's the DC gain going to be? You want to know how to get the gain? So, well, V out over V in .949, the gain at this voltage, okay? So using all those equations, we can get to our DC gain there. One important thing to note, this is going to vary for different voltages slightly, okay? So this variance will be minimized in a well-designed power amplifier, but it will have some variance. So here's an example. We have 0 up to 10 volts in your V out, and the associated calculated input voltages, and you can see the gain changes there from 0.94 up to 0.99, okay? So that gives an idea of the linearity of your power amplifier. So in this case, you could say across this range, we have a linearity within about 6%, okay? As we go from around 1 to 0.94. So pretty good, but of course you can always design things to minimize that if that's the constraint you care about the most. So we'll just have a little bit on output resistance. So how do we get the output resistance of our amplifier? So if we assume all of our voltage sources are ideal, which we typically do when we're looking at the output resistance calculations, and we can redraw our circuit as here, so everything's grounded, simplifies the situation quite a lot. And we find that the output resistance is just the emitter resistance of both the transistors from their small circuit models here, so the REN and the REP. Okay, so we can obviously redraw this left side as this, and we can see that we have these resistors in parallel. Okay, so REN in parallel with REP. And you'll know from your small signal models, REN is equal to your thermal voltage divided by that current, IN, going through here, so that will be equal to IE there. And same for REP, but with the current IP. So if we plug those into our Rout equation, we get this expression here. This is in parallel. If you draw that out, so of course you have your R1 times R2 over R1 plus R2, it will simplify down to thermal voltage over the sum of the currents. Okay, so pretty easy to calculate your output resistance there. This does take in some assumptions. So here we're assuming, we know that an increase in IN will lead to a decrease in IP from our equations earlier on and how they relate to each other. So that means that your R out is actually going to be fairly constant. As we increase one of these, the other decreases. That value on the bottom stays pretty constant. But that's only true for smaller input voltages. If you get to very large voltages, then IN or IP will start to dominate. Okay, this is true for the smaller signals around the quiescent point. So then R out, if one of these gets particularly large, R out will decrease. Okay. Okay, so how do we actually bias? So in our theoretical, nice and easy to analyze class AB circuit, we just had the VBB over 2 as power supplies. In reality, we need a better way to bias them, ideally a power efficient way. So one approach is to bias with diodes, okay? Just like we've done before with voltage regulators and things like that. So here we have a current source, and this current source is going to supply the current needed for the diodes to operate at the defined voltage that you want for that bias, and also needs to supply the base current to your QN here. Of course you want that current source to be as low as possible because you want power efficiency, right? So you don't want to kind of overspec your I bias. These diodes, by the way, they could be actual diodes or they can be transistors, so 3-terminal devices, but with 2 terminals linked to act as a diode, okay? So your quiescent current here is going to be equal to N times the I bias. So the thing to note here about the design is that N is the area ratio of the junctions of the BJT and the diode, okay? The reason that becomes important here is because with power amplifiers, you typically use power BJTs, So they might have much larger junction areas, so they can handle much bigger currents, right? But you don't need such large junction areas for your diodes. You just want regular diodes for your power efficiency. Otherwise, you're wasting a lot of power over the diodes there. So your diodes can have much smaller junctions than your BJTs, but that difference in junction area between the diode and the BJT, N, will affect your quiescent current, okay? So it all comes into how you calculate your currents and your efficiencies. So N is the ratio between the junction areas between the diode and the transistors. So as Qn, sources current, from the sources current to the load there, then it's going to need an increase in its base current. So that's going to be whatever this current is here divided by, approximately divided by beta, okay? So the very minimum, like I bias is obviously constrained by the need to give sufficient base current here, okay? So if you know what currents you need here, that gives you some information of what kind of I bias you're going to need, because you need to be able to cover the IB, the base current of Qn, and also the current through the diodes. So the absolute minimum there needs to be more than the IB that you need. So N can't be too large, otherwise this condition won't be met. Okay, so just rearranging that equation at the top there, we have N is equal to your quiescent divided by your I bias. So if you have a very large N, which you want because you want to use your smaller diodes for your efficiency, then you'll need a very small I bias, and that might not be enough to supply the base of your Qn there. Okay, so these are just the constraints on your design. And this is something that in discrete circuits is very hard to control, because you can't just change the junction area of your diode. But if you're designing an integrated circuit where all of this is strictly designed in the semiconductor level by you, then you can control that junction area. Okay, so when power amplifiers can obviously come in ICs, and they'll have all this design taken into consideration. So a quick question for you. Here we have a diode biased AB power amplifier. We want to ensure that there's 1 milliamp minimum current going through the diodes. What should the I bias be? So there's no hints to come up in this one. It should be straightforward given the information that you've got. No answers yet. Oh, there we go. There's one. One incorrect answer. I'll give you another 30 seconds and I'll go through it. Okay, I'll go through this one. So we've been given, we need to get our 1 milliamp minimum current through diodes at all times. So we need to consider the worst case scenario where the maximum current is going to come through on the output. Okay, so our max current draw through IB. So that's pretty straightforward here. I load max, because you're given that peak output voltage of 10, so that's going to be equal to your 10 volts over your 100 ohms. That would equal 100 milliamps. Okay, and that's, in this case, essentially equal to your IE. Okay? We have a positive output, so we're just concerned with our Qn, and that means that current's being drawn from IE there. But we're interested in the IB, so we know how to relate those. IB is equal to IE over 1 plus beta. Okay? So, again, that's somewhere where people can slip up if they just divide by beta. That will give you your IC. So here we've got the IE. So that would be for IC. This will equal 1.96 milliamps. Okay? So we need, at most, at our base terminal here, 1.96 milliamps. But we also need 1 milliamps to go through the diodes. Okay? So that means our I bias will need to be just the sum of those. So 2.96 milliamps. Okay? Then you've always got sufficient current to cover your base requirements and keep the diodes running at 1 milliamp. Okay? Make sense to everybody? So now if the biasing diodes had 1/3 the junction area of the output transistors, what would the quiescent current be? So we know our I bias is equal to 2.96 milliamps. And we know from our equation earlier, IQ equals N times I bias. And if our diodes are 1/3 the junction area, then N is 3. Okay, N is how much bigger the BJTs are compared to the diodes, so they're 3 times bigger. So that just becomes 8.88 milliamps. Okay, so you can work out the quiescent current that way, which of course comes into your power efficiency. So how much power is going to be used in that idle state. So fairly straightforward, simple approach to biasing, but as you can imagine, you don't, if you're building a circuit, as I said, in discrete components, you don't have so much control of that N. Okay, your junction areas are not really in your control. So in IC design, they might be. In breadboard circuit or circuit board, protoboard design, probably not an option. So we'll also look at the alternative, or an alternative, which is biasing with what's called a VBE multiplier. Okay, so this is just another way to set up that bias voltage to convert your class B to class AB. So you can see we still have a bias current up here, still supplying to the base of Qn, but now we have this little circuit with an extra transistor and 2 resistors. Setting up at these terminals here, there's your VBB voltage. So here, for maths simplification, if we neglect the base current of Q1, so this current here, which we expect to be very small, especially if beta is high, okay? Because that's, of course, basically that's IC divided by beta, so it's going to be a small current. Then we can show R1 and R2 should carry the same current, so we've just simplified this circuit by saying, don't worry about this, we've just got this one IR current coming through here. And then that means we can show that IR, this current, is equal to your VBE across divided by R1, okay? Because VBE is that voltage drop across those 2 terminals, and there's your resistor. So that's one way to simply calculate your IR. And plugging in that top equation, we can then show that VBB is equal to VBE1 brackets 1 plus R2 over R1. So you can see why this is called a VBE multiplier, because your VBB voltage is VBE multiplied by some factor, which you can control by changing your R2 and R1 resistors. Okay, so in your discrete circuit, you have full control over that. You just need to know what your VBE1 is, and you can design for any VBB that you want and adjust your bias just by tweaking those resistors. They could be potentiometers, you could make that adjustable. And of course, by choosing your VBB, you can get the IQ that you want, the quiescent conditions, to fit whatever design spec you've been given. So the value of VBE1 is determined by the portion of I bias that flows through the collector of IC1. So IC1, this current here, is going to be I bias minus IR. And again, we're neglecting these base current inputs for now, because they're typically going to be much smaller than the other currents that we're interested in for this solution. So then if we convert that equation, we get VBE1 equal to VT log IC1 over IS1. So another class exercise. Here we've got the VBE multiplier, equal resistors 1.4K. You're given the VBE and you know the IC. You can assume beta is very high. So of course that means you can neglect our IBs. What value of I bias is needed? Okay, a few more seconds. Alright, so we have 1.428, that's the correct answer. And just to go through that, so we know, as we just showed, I bias is equal to IR plus IC1, and we have IC up here. So we just need to find IR, and there's a couple of ways to do that based on the previous equations. So we can just use the VBB, which we know is equal to 1.2 in this case, equals IR R1 plus R2. Of course, we have the R1 plus R2 information. So IR comes out to equal 0.428 milliamps. Once we add our IC1, then 1.428 milliamps. Okay? Pretty straightforward. So that's all we're going to cover on class AB. So we've covered a lot on the power and efficiency on A and B. We've covered a bit more on how you get the different circuit characteristics and the transfer function of AB. So you can, of course, use the same approaches between all those different classes to solve any questions we give you, hopefully. And now just to cover very briefly class C amplifiers. So these conduct for less than half of the input cycle. Conduction angle is less than 180 degrees, less than pi. These can be very efficient. They can be up to 90%. There's not such a clear calculation for optimizing class C efficiency, so that's a rough figure. But ones you can buy can approach that. But obviously there's a large amount of distortion because you're losing a lot of your signal. So pretty much never used for audio amplification. And these are actually just used really in RF applications such as RF oscillators. You'll see that we have an LC circuit up here, okay? So that's a tunable circuit that you're tuned to the resonance of your signal in your RF application where you have a specific frequency of interest. And what that can do with your tuned LC circuit is turn your initial output, which is a limited, only positive wave where you've already lost some information. The LC circuit can turn it into a full peak-to-peak wave, right? But of course, this information is all sort of just replicated from here. So this is reliant on your signal being something like RF transmission, where you have a carrier frequency, which you know and you can tune to, okay? And then you can recreate the signal here, and you get much better power efficiency. So we won't go into the details of those, but just so you know they exist and the kind of applications that you might want to use a Class C amplifier. So not a true signal, and you can get a lot of distortion in there. So finally, little discussion on the remote lab. So I don't know if any of you have tried it yet. I'll do a poll in a second just to ask if anyone's logged in. But I just want to remind you all it's happening this week and next week. So as I said at the beginning, don't turn up to your lab sessions unless you want to consult with the tutor or you want to use the computers. But there's no requirement to come to the lab time slots. You can do it all remotely. You can manage your time however you like. But you just have to complete the worksheet, fill in all the answers, and submit by the end of week 11. That submission link is already up there. So just for your knowledge, this is the hardware. So when you play with it, it looks a lot like a circuit simulation. And you might think, this is LT Spice, I'm just messing around with a dodgy version of LT Spice. but it's actually hardware. Okay, so one piece of hardware is operating for all of you at once. So even if you are both, say 2 of you are logged in, every time you make a click, it resets that circuit, all of the switches and conditions to the ones you've set. It grabs the output and sends it to you. Okay, someone else clicks and it resets to their conditions, grabs the output, sends it to them. All right, so it's quite a sophisticated little bit of hardware. Obviously, there's a lot of efficiency in trying out a lab like this. So one piece of hardware you can all use simultaneously. You may experience some slight delay when you click before the scope updates, right? Especially if you're off campus. And if 20 users are on at the same time, there's going to be some small delays, maybe up to a second. But as you're normally doing something and then you want to look at those scope signals and work out what's happened, the delay shouldn't be a problem in terms of the learning from this point of view. So just a few notes on it. Remember, access anywhere online. But if you're off campus, you need to use the VPN. I think Binesh sent out instructions on how to get that. You can also just Google it, Macquarie VPN. Now you've all been approved. Students don't normally have VPN access. So that approval will probably be time only for the duration of this. But it does mean you can access this from your home, from anywhere you want. You can turn up, as I said, for the first hour of your lab session, consult with the tutors if you want to. Do complete it individually. So do your own worksheet, log in yourself, even if you're sitting next to somebody and you're chatting to them and they're doing the work and you take the answers, because we can see everyone that's logged in and every click they make, we'll see that you never logged in, right? Or we'll see that you logged in, turned a switch once and then logged out. So it's very easy to detect if someone didn't do their own work on this, which is a benefit for us. We can make sure everyone's doing the lab themselves. The worksheet's already on iLearn. As I said, you submit by the end of here. So it looks like we've got 50-50 maybe at the moment. I've actually logged in and tried it. So I, as always, please manage your time well. Don't leave it till, I know you will, but don't leave it till the last day to do it all. I don't think it's too complicated a lab. So I've done the worksheet and reviewed it after Binesh finished everything. Didn't take me too long to work through, and I'd never used a remote lab environment before, so I was in the same boat as you guys. And what are we at there? I don't know how it's going. The no was increasing so much. All right. And yeah, just to give you an idea of what you'll see if you haven't logged in yet. Okay. So this is all, remember, communicating with real hardware. You can adjust your frequency of your function generator, change it to square, sine, or grounded, amplitude, offsets. You can click on switches here, and they'll update. You'll see them change. You can move this little arrow on a potentiometer, change the resistance, and you can click any of these wires and move where they go into these points, right? So you can scope, this is your oscilloscope channels down here. You can scope any part of the circuit, and this is physically changing switches to make these connections, and then it will show you the output on there, and that will be the real scope output. Okay, then you have to work through the lab and solve all the questions. So it's all power amplifier based, class AB focused, but you actually switch from B to AB within the lab and look at and calculate the efficiencies and things like that. One thing I want to note as well: when you close your browser, you'll lose the setup. Okay, but it's actually quite a simple circuit. There's maybe, I think, 4 or 5 switches and a potentiometer, right? And then just your cabling. But what I would suggest, because you can obviously do this in one run if you've got a couple of hours, really just smash through it. Or you can do a bit now, a bit tomorrow, a bit next week. But if you close your browser, I would screenshot your setup so you don't forget. Mark where you are in the worksheet. Take a screenshot so you know exactly where you're up to. Or otherwise you have to follow back through the worksheet to make sure you had the setup as intended. And the key one to remember there is a potentiometer, there is a sliding arrow like this where you can set up the biasing. And that's, the value of that isn't shown on it. You have to probe it to get the value, right, under the right conditions. So make sure if you leave it and come back and you want the same biasing, that you repeat that step and check the biasing, okay? Don't just log back in and assume everything will be as you left it. So that's one downside. I'll see if they can work on having a way to fix that for the next iteration, but at the moment, just be aware of it so you don't work through half the lab with the biasing set wrong or something like that. Okay, so yep, I encourage you all to try that, and yeah, ideally your lab hours would have been 3 hours a week, so this should certainly not take more than 6 hours. Should be considerably less. Do you have a question?
I see on the weekly plan we have in week 12 and 13 we have a kind of practice workshop. What's that?
Yep, so we're going to be providing you with more practice questions on the various topics, and you can come along to the lab session then, and the tutor will help you if you're struggling with the questions. So we'll give you the questions but not the answers, and the tutor will know the answers so they can help you. So it's just basically revision practice questions.
Yeah. Will we have the mini exam on week 11 or 12?
So it's the week after next. It should be scheduled.
It says on the weekly plan it says it's week 12.
Yeah, so that should be right. So next week we have system integration, and then the week after we'll have that. Yeah. So, but we'll be sending announcements to make sure everybody's aware. I'll try to keep starting these a bit delayed. I'll send an announcement on that as well, but I need to see how much content we have to cover next week in case we need the whole 2 hours. But yeah, I'll try to start it delayed so everyone has time to get here. And the exam will only be 1 hour, so we'll probably start a little bit late there. But we'll also be asking for your TED survey feedback in that one. I know that's annoying to do, but it helps us a lot to get the feedback and try to improve the course. Okay, thanks very much, everybody. And don't forget the assignment deadline is today, okay?